All right. So we stopped at this point where we introduced new variables, right? Introduce new variables. Let me present. All right. We stopped at this point where we introduced new variables. Now we could, and let me put it like this. We could find the values of Q from X using selector matrices. So how do we do it? We just multiply X by C sub Q, and we multiply X by C sub V to get Q and Q dot. Of course, here, I guess like more correct it would be said that what we would find is this difference, right? We could find, for example, if we select C sub Q to be equal to, let's say, identity and 0, right? Block matrices. Then what we'll find is Q minus Q0 will be equal to C sub Q times X. Well, that would be what we could find, realistically speaking, using the selector matrices. Then if we insist on finding expression for Q, the final expression would look like this. The final expression would look like this. Same with Q dot. Q dot would be C sub V times X plus V Q dot 0. Okay. Well, that's a more correct way to describe it. But yeah, my point here is mostly that just as we describe X as a function of Q and Q dot, you can describe Q and Q dot as a function of X. Okay. Now we need one more variable to introduce, and that is we need to introduce the function phi, the function of Q dot, Q and tau, which would be equal to Q double dot, right? Phi is a function, is Q double dot. How do we introduce it? Well, let's go back a slide. So notice that we could express Q double dot from here as long as the matrix H is invertible. Then we just transfer everything else to the right-hand side, multiplied by H inverse, and we get Q double dot. Well, H happens to be always invertible for any mechanical system where Q is a true generalized coordinate. So, for example, system has n degrees of freedom. Q is n independent generalized coordinates. Then H would always be invertible. So for classical systems such as Lagrangian systems, such as like manipulators, robot arms, 3D printers, etc., it would always be the case. You can imagine more complicated cases where the coordinates that you choose happen not to be generalized coordinates, so they're not independent, for example. Then you can have trouble. But for simple cases, usually you would have your generalized coordinates, and H would be full rank matrix, so it would be invertible. Okay. Now, we can describe this expression phi, which is Q double dot, as I said, we put everything to the right-hand side, right? like C Q dot minus G, all of this went to the right-hand side. And we multiplied everything by H inverse. So we got our final expression for phi as H inverse times tau minus C Q dot minus G. Now we could write our dynamics in the state space form. So we could try to get closer to using X. So remember, this is X. Let us find its derivative. So X dot, together it will be X dot, right? What's the derivative of this function? Well, the derivative of Q is Q dot. The derivative of Q dot is Q double dot. So phi. So that's what we had. This change of variable 18 is completely standard. It is not even change of variables, but this kind of trick. So please take note of it. We deal with second order systems in mechanics. So systems with double dot, right? You cannot, like, you have a little bit of trouble when you convert them to state space, because state space is a first order system, but mechanical systems are second order systems. So the trick is to introduce this state variable. When you take a derivative, one of the states, so position variable, which was originally position variable, its derivative becomes velocity variable. And second one, which was originally velocity variable, its derivative becomes acceleration variable, all right? So you have the situation where you have the same variable here and here, right? Or once you take a derivative, you would basically have Q dot equals to Q dot. Like, if you actually open the brackets on the left-hand side, the first equation would be Q dot equals to Q dot. So it feels unnatural. But as soon as we replace this with X dot, it becomes natural. Like, we replace it with X dot, and Q dot becomes just a selector matrix times X, right? So now it is natural. Now it looks natural. So that is the way we do it. And this guy here can be rewritten in terms of state variables. So it can be rewritten as phi of X tau, right? Same function, just in terms of X, not in terms of Q. Now, expression 19 is exactly the same as what we have seen in the beginning. So technically speaking, you could already do linearization. Just do Taylor expansion of 19. But let me continue explaining, because there are still underwater rocks which we can run into. So let us be careful. Okay, so if we want to take a derivative of this whole thing, like of this function, here is what a partial derivative would look like. The matrix A would be derivative, let me go back, of this guy with respect to X. But X, remember, is equal to Q dot, right? Q dot. So we will take derivative of this guy or of this guy, right? With respect to Q and Q dot. Okay. So derivative with respect to Q here is like dq dot dq. It is 0. With respect to Q dot, it is dq dot dq dot. It is identity. Here it is df dq. We cannot simplify it. And here is df dq dot. Okay. Now, for the B matrix, what we have is, on top of it, it is dq dot d tau, happens to be 0. And d phi d tau. Well, this in this case, it is actually H inverse. Why is it a H inverse? Let's look. Well, this is how it looks. H does not depend on tau. So when you take derivative with respect to tau, tau goes away, you just get H inverse remaining. So in this case, you can find it without taking derivative. And it is very nice. You don't want to take more derivatives than you have to. So in this case, it is quite simple. Okay, let's go on. Now, the problem is we need to find Jacobians, d phi dq, d phi dq dot. How easy is it going to be? Well, d phi dq is basically d dq over this expression, H inverse times tau minus cq dot minus g. This is a multiplication of two functions of q. This function and this function. Okay. Now, how do we take derivative of a product? Well, derivative is the first member of the product times the second one plus the first member of the product times derivative of the second one, right? Now, I didn't stress it before, but let me go back. We often assume that we take as a linearization point the point where this expression C of q dot 0 q0 times q dot 0 plus g of q0 is equal to tau 0, right? So basically, we take such a linearization point that this guy and this guy would cancel each other. And given that q is full rank, h is full rank, it implies that q double dot is 0. So basically, around the node. That is a fancy way to say we are talking about a node. But here we can be more concrete because, because H is full rank, basically. All right. Now let's go back. So since we're talking about this linearization point, we said that this is equal to this. But you see here, what we have is tau minus this expression, cq dot g, right? So in fact, if we take a linearization point, as we suggested, so this type of linearization point, then this expression would go to 0 if we linearize around the node. But since it goes to 0, we don't need to evaluate this guy either. So that is a big advantage of linearizing around a node for a mechanical system. You don't have to linearize the inverse of a matrix. So you don't have to take a derivative of the inverse of a matrix. It is in fact very possible to take this derivative. It's not crazy. The derivative of inverse of a matrix is like, it would be H inverse times dH dq times H inverse with a minus sign in front, if I remember correctly. You don't have to memorize this type of formula. It is easy to find on the internet. But so it's possible to take this derivative. It's not crazy. But computationally, it's going to be even more work. Like, you already have some work computation, you'll make even more work for yourself. Like, do you want to do it? Good question. And practically speaking, often enough, more work means more computations, means slower process, means slower control system. that is bad, usually not what we want. So being able to cancel this term is very nice. And that is what you achieve by linearizing around a node. Okay. Of course, this doesn't necessarily imply that, how should I put it? You can achieve the same thing as long as this holds. So it doesn't have to be a node. If it is a trajectory, but this somehow holds, fine. But you have to be careful about how you define such trajectory and so on. Yeah, but you understand the trick. The trick is to make sure that this term cancels. Right? The trick is to make sure that this term cancels. For a node, it is obvious what's going on. Yeah. Okay, all right. Now, with this term cancelled, we have dphi dq equals to h inverse times dh dq of this term on the right-hand side. Now notice that d tau dq is essentially 0. So this term, yeah, here I think it's a mistake. It shouldn't be this term. And you have two derivatives. You have dc dq, right? So this guy, and dg dq, so this guy. Well, this, when you look into it, you'd find that this is like basically Jacobian. It is quite doable to find it. Well, this guy happens to be one of the worst part of linearization, because C itself is, to compute it, you have to compute what we call like Kronecker symbols, or depending on how you do it, you can also compute it through first derivative of H. So it depends. But basically, it's C is already full of derivatives, partial derivatives. And here you're asked to take one more partial derivative. In terms of computations, this part is the worst. Is pretty bad. But yeah, you can do it. You can do it. If you're going to do it in practice, I would recommend to do either symbolic math or auto differentiation, just for your original practice. But there are also analytical solutions for this, as an analytical algorithmic solutions. So if you want the fastest result, you should look into how it's done analytically, like geometric methods and so on. But auto differentiation, let me write it here, is a good approach. So if you are going to do it, for example, you can use Casari. That's the software package that does auto differentiation. So if you're going to try to do it, yeah, try to do it with Casari or symbolic math in MATLAB or SymPy in Python. There are possibilities. All right, now last step that happens to be easier. dphi dq dot. Well, it is ddq dot of the same expression. But now notice that this guy does not depend on q dot. It's not going to be cancelled, but we don't have to take a derivative of it. This guy doesn't depend on q dot. This guy does not depend on q dot. So we're actually only taking derivative of this guy. So it is dc q dot dq dot times this guy, minus sign from here. Well, let us please not assume that this is equal to c. This is not equal to c, because c itself is a function of q dot. So this is actually a quadratic form, and this would be a derivative of a quadratic form. Yeah. But c depends on q dot in certain way. So, like, you can do it analytically, of course, but you have to be careful. Yeah. But this expression, computing it will be easy. Okay, that is it. That is it. That is how this differentiation is done. How differentiation is done. Let me check here. This last slide. So let me summarize. When you are going to work with mechanical systems, your A matrix would look like this. Your B matrix would look like this. It is possible that here you would also have additional matrix which would come from you having underactuated systems or something. That is not, yeah, is not like a very big deal. Yeah, this guy very hard to compute, but you can use auto differentiation to compute it. That is simpler, but still not trivial. To compute this guy, we also use this trick where we linearize around a node. Without that, you would have even more computations, which have to do with taking derivative of inverse of a matrix. Overall, if you don't like this, if you say, okay, I don't want to deal with it, you can go back here, look at this expression, and say, how can we find the linearization? So Jacobians, without doing differentiation. And then you remember finite derivative method. So what you can do is, for example, just take x0, vary it around, find variation of x dot 0, and find the linear relation between variation in x and variation in x0. Finite difference method. I'm not going to discuss it right now here, but it's possible to compute derivative approximately using finite difference method. The quality of such computation would be high enough. It's not as good as analytic expressions, but analytic expressions have their own drawback because they compute a lot of functions which are inside other functions, so they accumulate error in their own way. So it's not always clear which one is preferable. Clearly, coarse numerical differentiation can be a problem. Clearly, it is a problem for rapidly changing dynamics, and so on. So it's not ideal solution, but it can be done. People use it. It's fine. Numeric differentiation, right? Finite difference method. Yep. But that's it. As you can see, it is not very crazy. There are a few scary looking expressions here, but in the end of the day, if you do it in software, it's fine. Yeah, it's fine. There are software solutions that do it for you. And for example, one of the software solutions that does it for you is like Pinocchio. That's relatively famous, but there will be numerous solutions that would try to provide you with linear models. All right, that is it for today. I apologize for the break in the middle of the lecture. I'll stop the recording and we can ask any questions.